Hello and welcome to today's Wolfram Institute livestream. Today we have Furkan Semih Dünbar, physics PhD out of Bogazici University with a thesis in quantum phenomenon and shape dynamics. He's an associate professor at Amasya University. Hope I'm pronouncing that correctly. And
Yes, correct.
since 2025, he's been an affiliate researcher with the Wolfram Institute. Today, Semi will be talking about quantum operators from the Wolfram model, multi-way systems. Semi, go ahead.
Okay. Thank you, Dugan, for the introduction. Good morning, good afternoon, and good evening, depending on where you are. So welcome to today's seminar. As Dugan said, today I will be talking about quantum gates from Wolfram model multi-way rewriting systems and share what we have found so far. What we are doing may be called as computational philosophy, and we interpret Leibniz monads in terms of competition, and uh, we see that using the Wolfram model multi-rewriting systems, we can encode quantum operators like the C0, pi 8, or the Hadamard gate. Uh, Once we have a multi-way system, we will see that we can represent a family of S matrices or the transition amplitudes for states using that multi-way system. So I mentioned it in a previous seminar, but for completeness, let me talk about the distinction between Leibnizian and non-Leibnizian strings. Non-Leibnizian or Leibnizian. The idea that in a Leibnizian string, each character in the string is distinguished locally from other characters, but in non-Leibnizian ones, there are at least two characters that share the same neighborhood, even if we exhaust the whole string. For example, let me give just two examples. A trivial example for non-Leibnizian ones is the following. Let's say we have 6 consecutive A's. The neighborhood of this, the maximal one becomes, let's make like this file. There is no difference between this A, or this, and this one. By the way, we are imposing a side boundary condition, so the character after the last character is the first one, and the character that comes before the first character is the last character. So keep that in mind when we are talking about strings. On the other hand, for Leibnizian ones, let's say an example would be like, so in a Leibnizian string, each character is distinguished locally in terms of neighborhoods from any other character in the string. Okay,
So
let's
is
consider
that is
these.
that just saying that each character is different than its neighbors, or that um, if you look at what the string looks like relative to a particular character, like what is the neighborhood exactly?
Actually, okay. In order to compare the neighborhoods of two characters, we need two characters. For example, if we compare A and B, they are distinguished already at the zeroth level. So it's
Mm-hmm.
enough that we compare letters of the same type. Let's consider this one and say this. At the zeroth radius, they are the same. They are the same letter A. And when we enlarge neighborhood to this and to here,
Mm-hmm.
the neighborhood becomes BAB, and that one has BAA. So they are not the same. That means that they are distinguished. That's what I mean by they are distinguished locally.
Okay.
By the way, okay, when comparing neighborhoods, we say that two neighborhoods are isomorphic if, let's say, N1 is the same as N2, or one is the uh, other one when written in the reverse direction. Let's say it's transpose. So this is what we mean by string isomorphism, or to say that if two neighborhoods are the same. So that's the jargon. Okay. Leibnizian strings makes it possible to model its constituent letters as Leibnizian monads. So that's why we have the word Leibnizian for such strings, because in the Leibnizian philosophy, monads are like some metaphysical atoms of the universe, unlike the hydrogen atom. It's a bit more, let's say, abstract, to say the least, because each monad is, let's say, is indicated by its view. And in Leibnizian strings, we can define the view of a character as the smallest neighborhood that distinguishes it from any other character. For example, for this case, the view of this A is that one, and the view of this A is this one. There's a trivial non-Leibnizian string, which is of this form. Let's say there's a single A and the rest is B. I call this non-Leibnizian because what is the view of A? It's already distinguished at the zeroth radius. And so its view is just itself, and it's not connected to the rest of the universe. So that's kind of a choice, maybe one may call it a choice. So we also call such strings where there is only single occurrence of a specific letter in the string. They are also non-Leibnizian. So that's kind of the basic distinction between Leibnizian and non-Leibnizian ones. The idea to keep in mind is that Leibnizian strings may allow us to interpret them in terms of Leibnizian monads. And we will see that the occupation number of monads in terms of their views kind of exhibits Fermi-Dirac like statistical distribution. So yeah, they may be called as fermionic. Okay, this is the distinction between non-Leibnizian and Leibnizian strings. And in this study, we considered Leibnizian strings all over in the work. Then we define what is called as the Barbour Smolin. I think there's S. This is a function. It measures the amount of structure in a string. It's called as the variety function. And it's defined in the following way for Leibnizian strings. And I think it's also possible to generalize to non-Leibnizian ones. But yes, today we are only considering the Leibnizian strings. Okay, let's consider the word we have written there, which is AAP, AAB, ABB. First, we define what is called as a relative indifference. This is defined for two distinct positions in a string. Let's call it Rij. Let's say this is the, let's go to the previous example, Ij. This is I and this is J. We have seen that they are distinguished at the first order neighborhoods, which means that the radius is 1. So the relative indifference of the characters A, which occur at position I and J, this is just 1. When we consider another example for the same word, let's say this is I and this is J. At the first radius, the neighborhoods are B, A, and maybe one is the reverse of the other, so that means they're isomorphic. So we go one more step in the neighborhood, and we obtain the second radius 2 neighborhood, which should be BB, AA, E, and EAA, EAA, EA. As you see, these are distinguished because one is not equal to the other one, or one is not the transpose of the other string. So that means R12 is 2. And this is R1, 1, 2, 3, 4. R1, 4 is 9. So this is the definition of relative indifference.
Right, and for non-Leibniz strings, then you'll have R values of undefined or infinity.
For non-Leibnizian ones.
Uh-huh.
For those, the two radii are not distinguished. So you may also say that it goes to infinity, or you just mark it as a sign of non-Leibnizianness and proceed in the calculations accordingly. So yes, that's kind of the idea.
Right. So, but in any case, that's why we're looking at Leibniz strings in this case, so that we do have well-defined R values for these.
Exactly. Yes.
Kieran has
Another
a question.
motivation. Sorry.
So could you please go up a little bit?
Yes.
Yeah, those initial strings that you showed, AAAAA and AAB, ABB, which one is Leibnizian and which one is non-Leibnizian?
This is the Leibnizian one, and this is the non-Leibnizian.
No, okay. And a string, let's say ABABA, would that be Leibnizian or non-Leibnizian? AB.
Let me write
A.
AB.
ABA.
ABA.
Yeah. Because the B has similar neighborhoods in both instances.
Yes, this is non-Leibnizian.
Oh, okay. And one quick clarification: what is the transpose of N?
It's the string written in the reverse order.
Okay. Thank you so much.
You're welcome. All right. They talked about the relative indifference. Then comes the definition of absolute indifference. It is defined for a single position in the string, or let's say for a single character, and it is the maximum of relative indifference values where J runs over all the characters except the ith one. So this is the definition of absolute indifference. In a way, it measures how the local neighborhood of a character is distinguished from the neighborhoods of other. Is defined as sum over 1 over A. So that means the local neighborhood is shared to some extent by other characters. So it kind of motivates the appearance of 1 over AI. So we penalize kind of the large. We use that definition, but of course, if you can apply any monotonically increasing function. I think you would still get some function that works in our study. We're just considering the base, let's say the canonical form. So that's the kind. To be defined action of as for completeness, I will briefly talk about what's called as the multi-way systems in the Wolfram model.
Wait, can you go back? Your audio cut out a little bit
Okay.
when you were describing the last definition. So we have the absolute.
Mhm.
What does that say?
Absolute indifference.
Indifference. Okay, and so that's the maximum
Yes.
radius that's needed to distinguish the worst case pair.
Mhm.
Okay.
It's the maximum of, yes, relative indifferences between
Mm-hmm.
another ones.
And then
Okay.
you have the sum of the inverses for the AI. What is that?
Yes.
Some sort of
This is called
variance?
as variety. Sorry?
Some sort of variance or
No, you mean statistically. I didn't think about it in this direction, but maybe I will think later on. This is called as the variety, the
okay.
Barbour-Smolin-Dodge variety.
Oh, I see.
It penalizes. Can you hear me now?
Yes.
When we have a larger value of absolute indifference, that means that the local neighborhood is not distinguished as quickly or as easily as from other neighborhoods. So that means kind of there occurs some similar structure, uh, although the string is Leibnizian. So it should analyze higher absolute indifference values. So that's why we have the 1 over AI. I also mentioned that instead of using 1 over AI, you may use some monotonically increasing function. So that would still do the same. Um, but yeah, we are using this one. It's also useful that this is a kind of rational number because AI is like integers.
Mm-hmm.
So that's also useful. Shall I continue?
Yes, please. Thanks for clarifying.
Sure. I will briefly talk about the multi-way system in the Wolfram model. The idea is that we have some initial configuration. It may be string, hypergraph, or another object. Then we define a real-guide rule that transforms some match patterns to some other patterns. So let's say if a rule matches twice, then there's a branching. In one of the branches, a single pattern is transformed. So let's say we obtain two different or two, let's say, related objects. If a rewrite rule matches only once, that means it transforms into a single output. If it matches, let's say, 3 times, then we have the object. Depending on the configuration and the nature of the rewrite rule, these events may continue indefinitely or they may terminate at some level. So this is the idea of multi-way system. As far as I'm aware, it's also called as abstract reduction systems, but yeah, that's a kind of comment. Okay, we have the idea of multi-way system. Then in our study, we focus on, let's say, the Leibnizian section of multi-way system. At the moment, we are considering some multi-way system. Let's make it. Okay, let's construct that one. Then, in our present study, the configurations are strings, which are arrays of characters. And given the multiway system, we focus on the Leibnizian part of the multiway system, meaning that if this is the full multiway system, we focus on, let's say this is Leibnizian, let's say these are Leibnizian, and these are, then we evaluate this this part of multiway system, and we consider this part. And we neglect the non-Leibnizian ones in the present study, but I think it may be possible to generalize it to non-Leibnizian ones, but the interpretation, I guess, will not be as clear-cut as we have here. Okay, this is the Leibnizian section of multiway system, so that's the idea. Now, we have a way to assign numbers to strings. How? We talk about the variety functions. So given a Leibnizian string, we can calculate its variety and we can assign a number to some abstract string. Then, if we can assign numbers to configurations, we can define an action on multiway system. For example, let's say let's say this is configuration A, this is B, and this is C. We are considering a single path, or actually we are considering a set of paths, but let's focus on some single path, Leibnizian path. Which goes from A to B to C. And we define the action for this path as follows. I'm using the same letter S for the action. And this is defined as minus the variety of A minus variety of B. There are a few things to notice here. We do not include the last configuration, and we are considering the negatives of variety. The non-inclusion of the last configuration is because when we will define the transition amplitudes and we will consider consecutive S matrices, and in order to kind of ensure a matrix product structure for composition of S matrices, we need to leave out the last configuration. Otherwise, it will be counted twice in the phase amplitude in the transition matrix or transition amplitude. The reason for negatives of varieties is because when we calculate the Hamiltonian, let's say an example Hamiltonian for a simple system, and if you want the energies to be positive or let's say non-negative, then we need the minus sign. But actually, we will have some free parameter k, which serves the notion of h bar. If you map k to minus k, then you can undo this negative signs, but this kind of some side comment.
So if there was a path that was like A, B, C, D, then you would
ABC.
the negative bars A and B
Yes, that's right.
out.
Yes.
And these multi-way systems. I mean, a priori, we could be dealing with any sort of writing.
Yes. But for the present considerations, we consider cyclic strings, and yes, that may be the. But if you define the variety accordingly for a non-circular string, then I think it should also be possible to do similar line of calculations. Let me check my notes. Um, okay. In order to define the transition amplitude between strings, we employ a variant of Leibniz's, sorry, not Leibniz, Feynman's path integral in the form of a path sum. And let's say form of the S matrices. When we have an inward and an outward, we define the S matrix element as sum over paths gamma. I will shortly comment on what these are. Let's say this is the inward, and there are some complex layers, and we have the outward. And gamma runs over all the paths that connect the inward and the outward. This S is the action we defined before. I mentioned the free parameter K is a free parameter, and we have the usual complex amplitude, so complex number I. So this is the definition of the transition amplitude for obtaining out string beginning with the in string.
And so the sum over paths from input to the output.
Yes, exactly.
Is this
okay.
contained within the Leibniz multiway?
Yes, exactly. We are only considering here the Leibnizian section of the multiway system. Actually, the K is free parameter. It's dimensions, but if you interpret these absolute indifference values as kind of length, so variety has kind of 1 over length units. So when interpreted appropriately, you may also construct the free parameter K as having units 1 over length. So that's kind of the idea. Okay, this is the general form of the transition amplitude. The simplest case is the following. We have 2 layers, consecutive layers. Let's say this is the layer 1 and this is layer 2. So in order to indicate gamma, we only need 2 numbers. The I, which is the inward, and J, which is the outward. Because in the action, we do not consider the terminal element in the terminal configuration in the path, these, or that system, will correspond to something like omega ji e to the I s I divided by k. Okay. Once we define the, actually these are weights and these are free parameters, real valued free parameters. Once we define this form for a S one another layer, say this is 3, we have the transition from here to here, then here to here. Suppose that S composites with the matrix of corresponding S matrices for adjacent layer. That brings out some condition on these pathways. And in this case, let's say this is C and this is J, and we sum over all the C because we are summing over all the paths, we need the following constraint for C of by omega.
Your audio is cutting out a little bit again.
Is it okay now?
Yes.
Okay. Maybe because I'm online on the university internet, so that may be why there are some. Okay, these two are the same form, and we impose, and this is the weight that connects the ith word to C, the word C, and the word at the end. So if we impose that, and by the way, while I'm adding another page, if there's any question, I'll be happy to answer.
Yeah. So the this exponential to the I, that's a different. That's the imaginary. You get phase.
DI here and that one, yeah, they're different.
The exponential allows the multiplication to be divvied up into additives.
Mm-hmm. So that's actually the sum of varieties of A and B. So that's kind of the exponential argument. Okay. It's okay. I'm going to give some examples, but maybe okay. Let's give some examples and let's refer to or yeah. Let's consider some applications. The Adama gate. This is a 2x2 matrix, which is of this form. 1, 1, 1, minus 1. And the multiway system that encodes this gate is this. We have two adjacent layers. This is what we call as interacting model in the paper. So this is the, let's say, first word, first inward, and this is the second, and this is first outward and second outward. The form of the S matrix for this multiway system is as follows: omega 1, 1, e to the I S1 divided by K, and omega 1, 2, or suppose these variety values of the first inward and the second inward are the same. That means we can bring up the phases to out of the matrix, and we write The phase doesn't have any physical, the global phase, of course, it doesn't have any physical significance. So we are left with this one. And omegas are real parameters, real valued parameters. So we can choose them in the way that they correspond to the other magnet. The let's say the important point to notice here is that, as I will speak about later on, is that a single multi-way system or some part of some multi-way system does not single out a specific S matrix, but at the moment it creates or it encodes a family of S matrices. So this is important to keep in mind. Okay, when we choose these real parameters as such that they will correspond to the other magnet. So if we have a 2x2 system with if the variety values of the first invert and the second invert is the same, so that multi-way system can encode the other gate among other gates. Okay. Yes, actually we do not single out a specific S matrix. Maybe studies in the future may restrict the family of S matrices by using some other, I'm not sure, physical or philosophical arguments, but that's what we have at the present. Okay, let's consider another example, the pi8 gate. We can consider the following model. We are considering 2x2 systems at the moment, and we'll touch upon the case for the 4x4s in a moment. Yeah, this is the first invert, second invert, first outward, second outward. Here, there is no transition from here to here and no transition from there to there. That means the corresponding omegas should be zero. So they are not included in the path integral, so they are just zero because the set is empty. Okay. The form of the S matrix for such a system will be in this form. And the off-diagonals are just zero. And we do the same trick. We bring out the complex phase at the beginning of the equation. And what we have will be, yes, S2 minus S1 divided by K, and is just zero. That global phase has no physical significance. What matters is just this delta S. And if we choose omega 1 as and omega 2 as ones, then the S matrix is correspond to this. Then, if this term is equal to pi over 4, then we can encode the pi8 gate. This is important because together with Adamar gate and the CNOT gate, if one can implement those, then as far as I'm aware, one can encode any quantum circuit, if I'm not mistaken. Because the variety is a rational number, so their difference is also a rational number. And on the right-hand side, we have pi. In order to bring out the factor of pi, one may consider like a reduced, let's say, k parameter, like k goes to k over 2 pi. So we can bring out the factor of pi in the denominator. So yes, one may consider these, or another approach would be that we may consider larger and larger words or strings their difference divided by k may approximate the number on the right-hand side. Okay, let's construct CNOT gate. And for that, we may have the following multiway system: 4x4, 4 inwards and 4 outwards. Let's construct such a connection structure. The S matrix that will correspond to that one will be okay, let's just suppose that all of the inwards have the same variety. So we factor out the global phase. Omega 1, 1, omega 2, 2, and 0, omega 3, 4, 0. So obviously, when you choose all the weight as 1, you obtain the CNOT gate. CNOT gate, iterate, maps maps such states when the control qubit is in the at 0 state. It doesn't change the second qubit. But if the first qubit, which is the control qubit, is 1, it applies the NOT gate on the side. So that means it maps 0, 0 to 0, 0, 0, 1 to 0, 1, 1, 0 to 1, 1, 1, 1, 2, 1, 0. So that's the reason why we have this elements here.
So the first qubit is control operation.
Yes.
Second.
Yes. This is also why it's called as CNOT, which means controlled operation. Okay. Let's construct another gate, which is not necessary for our purposes, but to be useful to illustrate a few properties of our systems. The swap gate. What it does is that it swaps the first and the second qubit. So we have 0, 0 goes to 0, 0, 1, 0 goes to 1, 0, and 1, 0 goes to 0, 1, and 1, 1 goes to. For that gate, the multiway system may be in this form, because we'll have off diagonals here, and we have this. We also suppose that all the variety values of the inverse are the same, so we can factor out the global phase. And the gate, the matrix representation is the following. Okay, I would like to touch upon an issue, or rather than symmetry, of the multiway system representation, because we do not have any a priori argument to order strings in a single layer. For example, one can, in principle, I mean, in terms of multiway system, construct this and let's say this system, when we interchange their places, then we will have such a multiway system. And that may correspond to the identity gate. So let me note that we have this symmetry at the moment, and that's one of the reasons, among others, why we have a family of S matrices. So let's keep that in mind. Let me check my notes if there's. Okay, so far we have considered two consecutive layers in the multiway system. We may consider some moderately kind of more complex models. Let's say we have three consecutive layers. We'll some off diagonals, and the second layer may correspond. The first layer may be represented by that apply on two qubits. Let's write sigma x. And the Kronecker product is this. One may also consider sigma y another Paul gate. And that would be step by step. And that should be -1, 1, minus. So it's also in this form. And that three-layer multiway system, I do not say it encodes, but it can encode the following case. Let's say you apply x to the first qubit, x to the second one, and we have the CNOT operation. This is CNOT. These are NOT gates. Or when we consider the Paul Debye matrices, then we would have similar looking circuit, quantum circuit. So yeah, these are the kind of two elements from the family of S matrices that can be modeled in our kind of system. Because we can represent the CNOT gate, the pi 8 gate, and the Adamar gate, one may emulate any quantum circuit by choosing an appropriate multiway system. So far, we have considered the string ontology, but one may also consider generalization of the string ontology to hypergraph ontology. So that's another future research direction. So far, we have considered the Leibnizian strings, and as a note, they kind of exhibit Fermi-Dirac-like statistics for the occupation number of monads or their views. So that's kind of the second idea. Another future research direction may be to consider non-Leibnizian ones as well. For example, when we consider such a string, we talk about at the beginning of the talk, there is no way to distinguish any letter from another letter in this case. Right? There is, of course, cyclic boundary condition. So, as a kind of guess, that may, or let's say that might indicate some sort of Bose-Einstein condensation, maybe. So, I think, yes, the concentrations of non-Leibnizian ones, the strings, may be useful in some context, which I'm not sure at the moment. And yes, so I think I completed my notes. And if there is another question, we can continue with questions, or we can end the seminar.
So what's the connection between the multiway system and these? Am I correct in that's the
So, if I understand correctly, you are asking the connection between the quantum gates and the multiway systems.
uh-huh.
Okay. Okay, let's begin with the fundamentals. We have the multiway system. We have Leibnizian and non-Leibnizian configurations. We are considering in the present study only the Leibnizian ones. So we include, we consider the Leibnizian part of the multiway system. Then, because we can assign a number to abstract strings using the variety function, when we consider paths in the multiway system, we can assign an action for that path. So once we have an action on a path, we can consider something like a discrete path integral, where we use this action as an kind of multiplied with the imaginary number I as an exponent, as the phase of each contribution to the transition element. Okay, so we define the transition element and we impose that the S matrix that connects first and the third layers can be decomposed as a multiplication of the S matrices between first and the second and the third layers. That brings out the condition on the weight functions omega. Okay, so we have that structure, and using some simple multi-way systems, we illustrate that we can encode, or let's say represent, a quantum gate, which is a unitary operator, using a multi-way system, considering the form of transition matrix, or the elements of the transition matrix you find, let's say, expressed in this equation.
Would that necessitate an equal number of elements, layers 1 and 3?
No, it doesn't necessarily. It's applicable to any other situation, but there may be some cases where it's impossible to find a unitary S matrix for the transition, because that in some cases the number of free parameters omegas are not, let's say, enough, and we need to enlarge the system by including some environment. But
Okay,
if the
so in
number of
general, these transition matrices not necessarily be.
no, not necessarily, yes.
Okay, so in that case they wouldn't be invertible as transition matrix necessarily.
We may include some semi-unitary matrix, and for example, let's consider some 2 by 3, and we computed transpose conjugate. Let's say this is 2 by 3, and the result would be the identity matrix I 2 by 2. So in some cases, yes, although they are not rectangular, sorry, they are not square, you may still find some semi-unitary matrices that satisfy some key properties. Mm-hmm. I think the present work is kind of interesting. Yeah, I think yes.
Yeah, absolutely.
Yes. One of the key points for future research, I think, maybe to consider these word ordering in layers. So if one can come up with some, let's say, a way to order these words and single out some specific S matrix, that may be another interesting research area, I suppose.
Ryan, Nick.
Yeah, not right now. Not right now. Thank you.
Thank you for.
Thank you.
Thank you.
Thank you. Thank you so much.
You're welcome. Thank you.